Today we're going to build through the Fourier series for a function to the Fourier transform. Then we're going to look at some properties of the Fourier transform and look at an application to differential equations. So let's start with the following inner product on the set of functions from the interval minus L to L to the complex numbers. And so by an inner product, you want to think about this as like a generalization of the dot product among vectors. Okay, so the inner product of a function f and a function g is defined to be the integral from minus L to L of f times g bar. So we need a bar here because this is complex numbers in the codomain. So we're taking the complex conjugate. Okay, so we're going to start with the following lemma, and that is that the set of functions, well, they're really complex exponentials, e to the I n pi x over L, as n runs through all integers, is orthogonal with respect to this inner product. So what do I mean by orthogonal? Well, that means if I take the dot product, or in other words, the inner product of two functions from this set, then I'll get 0. In other words, they'll be perpendicular unless they're equal, in which case I'll get some number. Okay, so let's maybe check that. So let's look at the inner product of e to the I m pi x over L with e to the I n pi x over L. So that's going to be equal to the integral from minus L to L of e to the I m pi x over L times e to the minus I n pi x over L dx. And I had to have that minus sign in there because I needed to take the complex conjugate. So now let's mash those together and we'll get the integral from minus L to L of e to the I m minus n times x over L. Oh, I missed a pi times x over L dx. But now notice if m is equal to n, then I just have a constant there. Well, the constant is equal to 1 because I have e to the 0. But if m is not equal to n, then, well, my integration will be different. So let's break this into cases. So, like I said, if m is equal to n, then I'm integrating the number 1 from minus L to L. That'll give me the number 2L. So here I have 2L if m is equal to n. Notice I could maybe tweak this inner product over here by putting a 1 over 2L if I wanted to, and then we would get the number 1 here, and we would have not just an orthogonal set, but an orthonormal set. In other words, it's an orthogonal set of unit vectors. Okay, so let's see what happens in this other bit. Well, now I'll integrate. So that'll give me something like this. I'll have L over I times m minus n times pi, and then I'll have e to the I m minus n times pi times x over L, where I integrate that or evaluate that from minus L to L. But then by the periodicity of the complex exponential, notice that I'll get 0 for that. That's because I'll get, well, the same thing plugging in L and minus L. So I'll let you check the details of that. So here I get 0. But this is exactly what it takes for this set to be orthogonal. Okay, so let's see what we can get out of that. Now we're ready to take our next step, and we're going to use linear algebra. This is like one of the cases where linear algebra is super helpful for just like a description of what's going on. Okay, so let's recall that if we've got v1 through vn, which is an orthonormal basis for v based off of the inner product given by this symbol right here, then we can take any arbitrary vector w inside of v and express it as a linear combination of the elements from the basis. Well, that's kind of the definition of the basis, but the coefficients of that expression is given by the inner product. So in other words, w is equal to the sum as k goes from 1 to n of the inner product of w with vk in the vk direction. Okay, so let's do a similar thing for functions like we had over here, where the inner product was given by this integral, I tweaked it a little bit to make this an orthonormal set. Like I said, we could have done before. And let's see if we can express functions like this in terms of this set right here. I hesitate to call it a basis because basis requires taking a linear combination which is defined to be a finite sum. But in fact, we'll need an infinite sum. And this is towards a Fourier series, and a Fourier series is obviously an infinite sum. Okay, so like I said, we should be able to write a function f of x from this kind of set of functions over here as a combination of elements from this set. So in other words, we're going to sum over all integers numbers cn e to the I n pi x over L. And then, well, what is Cn? Well, based off of this motivation over here, Cn is this inner product number. So in other words, Cn is the inner product of f of x with e to the I n pi x over L. But that's defined in terms of an integral. Notice that this is equal to 1 over 2L times the integral from minus L to L of f of x e to the minus I n pi x over L dx, where we got that minus sign from taking the complex conjugate. But now let's box this off, and then we'll take this expression for Cln and we'll insert it into this series expansion for f of x, which this series expansion will hold from minus L to L. Okay, so that means down here we'll have f of x is equal to the sum, as n goes over all integers, of the Cn, which I'll write like this. And actually, maybe I'll take this 1 over 2L out front, because I can definitely do that. And then I'll have an integral from minus L to L of f of y e to the minus I n pi y over L dy, where I've changed my variable of integration just because I don't want to overuse x's. And then we'll have e to the I n pi x over L. Great, so there's a somewhat complicated expression of our function f of x. But if we were looking for the Fourier series of our function of f of x, we would simply calculate these numbers right here, and then we would have our expression of f in terms of these complex exponentials. But that's not really our goal. Our goal, like I said before, is towards the Fourier transform, which it'll be helpful to express it like this. Okay, so next up I want to introduce a little bit of notation. So let's put that notation over here. And I want to set k sub n equal to n times pi over L. And then that means delta k will be equal to, let's see, pi over L. And then let's notice that that makes 1 over 2L equal to 1 over 2 pi times delta k. So I've got my 1 over 2L term here. That's why I needed to calculate that. Okay, so now let's see what we have from there. So that means we can write this as the sum over all integers of, well, we've got our integral from minus L to L of f of y e to the minus I times kny dy, and then e to the I knx. And then I'll have a delta k out here and a 1 over 2 pi here, where I've split up this 1 over 2L into those two parts. Okay, so now let's bring this up to the top and see where we can go from there. So far we've built up to the following kind of crazy expression for our function f of x in terms of a series that has an integral inside of it, so pretty crazy. So now what I'd like to do is note that, well, the role that L is playing could be tweaked. We could pick different values of L. So that motivates us to perhaps take the limit as L goes to infinity and see what happens. But let's notice that since Kn is defined as n pi over L and delta k is defined as pi over L, as L goes to infinity, delta k goes to 0. So that's going to turn this sum right here that looks like this, that's kind of like flanked by this delta k over on the other side, into an integral. In fact, what we really have here is a Riemann sum, or kind of a version of a Riemann sum for the integral that we get to write down. Okay, so let's write that down. So we'll have this 1 over 2 pi, which just comes down. And then we'll have the integral from minus infinity to infinity, because we're going over all integers here, of the integral from minus infinity to infinity, because we let L go to infinity, of f of y e to the minus I k times y dy. So the kn will turn to k. And then that is inside of this kind of outside integral. So we've got now e to the I kx dk. So we've got a y integral inside of a k integral. And so for this limiting procedure of the Fourier series, we have gained what is traditionally called the Fourier transform. And well, what is it? Well, it's this thing right here that I'm underlining in pink. So this is known as the Fourier transform of little f. So we'll set this equal to capital F of k and say that this is equal to the Fourier transform of f of x. So in other words, we could come down here and put like a little summary statement. So we have f of k is defined to be the integral from minus infinity to infinity of f of, well, this has a y in it, but I'm going to replace it with an x, e to the minus I kx dx. So that's how to arrive at the Fourier transform of a function. You integrate it after it's been multiplied into this complex exponential. But then reading this entire picture right here with the f of k plugged in, we get something called the inverse Fourier transform. And that would be writing f of x as 1 over 2 pi, and then the integral from minus infinity to infinity of f of k e to the I kx dk. Because that's exactly what this thing is if we replace the pink underlined stuff with f of k. So there we have it. We've got an integral which takes us from function to Fourier transform, and an integral that takes us from Fourier transform back to the original function. So in other words, we've got the Fourier transform and the inverse Fourier transform. So now let's look at a couple of properties of this. So far, we've built up to the Fourier transform of a function and the inverse Fourier transform given by the following two integrals. And we motivated that by looking at a Fourier series and doing some sort of limiting procedure. So I think it's really nice to look at that limiting procedure because it gives some motivation to why Fourier series, or I should say how Fourier series and the Fourier transform are related to each other. Now I'd like to look at some nice properties of the Fourier transform. So let's first look at what the Fourier transform of the derivative of f of x is. So let's maybe say that this arrow is doing the transform. So, well, we'll use our formula that we derived over here. So this should be equal to the integral from minus infinity up to infinity of f prime of x e to the minus I kx dx. So that should output us a function of k. Now, how are we going to attack that? We're going to do it with integration by parts. So let's see if we can get that set up. So we're going to set our u part equal to e to the minus I kx. And so that makes du equal to minus I times k times e to the minus I kx dx. And then we'll take our other part, dv, equal to f prime of x dx. But that means that v will simply be f of x. Okay, so now we have our integration by parts set up, and we can apply the integration by parts formula. So recall that that's going to be u times v minus the integral of v du. So let's see, u times v will be f of x times e to the minus I times k times x. We evaluate that from minus infinity to infinity. And then the integral of v du, well, we can bring this minus ik out. The minus sign will cancel with the minus sign in the integration by parts formula, giving us plus ik times the integral from minus infinity to infinity of f of x e to the minus ikx dx. Okay, but now let's look at this second bit right here and notice that the integral involved is simply the original Fourier transform, or the Fourier transform of the original function. So at least this bit is going to turn into I times k times f of k. Now what about the other bit? Well, here's where I'm going to introduce an assumption which I left off, and I think it's sometimes nice to leave off the assumptions for the start of a calculation, because then you'll see where you really need them. And in order for this to really make sense, we need the limit as x goes to infinity and x goes to minus infinity of f of x to both go to 0. So that would give us this entire thing is going to 0 here, because the e to the ikx term is bounded. Notice those all have size 1. So there we have it. If we take the Fourier transform of a derivative, we get this multiplier by I times k. But notice if we were to do that with the second derivative, well, we would simply have two products with I times k. It would be I times k quantity squared times f of k. And that's just by doing this one more time. But I times k quantity squared is minus k squared. So we get minus k squared f of k. Okay, so there's like a rule for the derivative and a rule for the second derivative. Let's do one more rule. Let's see what we get if we multiply by x. So we're going to multiply by x, so we have x f of x, and we're going to perform the Fourier transform of that. So we've got the integral from minus infinity to infinity of x times f of x times e to the minus I kx dx. But now if you look at this, where could this x have come from? Well, notice that it could have come from taking this complex exponential right here and taking its derivative with respect to k. But in fact, we would be off by a constant there, because that would have given us a minus I. So in order to fix that, we need to multiply by positive I. So in other words, this is equal to I times the derivative with respect to k of the integral from minus infinity to infinity of f of x e to the minus I kx dx. Because taking that derivative with respect to k only hits the exponential part, which would bring down to minus I times x, but the I and the minus I will cancel and just leave us with this over here. But notice that that's just the derivative with respect to k of the Fourier transform. So we can write this as I times f prime of k. Okay, great. So we've got these three nice properties of the Fourier transform. Now let's use them to solve a pretty classic differential equation. Now we're going to use those nice properties that we developed to solve a very classic differential equation. This is an Airy differential equation. And when I teach a first course in differential equations, well, we don't do the Fourier transform, unfortunately, but we do power series solutions to differential equations. And we usually attack this differential equation with the power series. Okay, so let's start with this. We've got y double prime minus x times y equals 0. So let's apply the Fourier transform and see what we get. So this y double prime will turn into minus k squared times what I'll call capital Y. So we'll take capital Y here to be the Fourier transform of lowercase y. And then, well, this x times y, well, we saw that that went to I times the derivative. So here we get minus I times the derivative of the Fourier transform. So that turned this second order differential equation to a first order differential equation. Furthermore, this differential equation that we have now is separable. So let's see what we can do with that. So let's move some things around and we'll see that we get y prime over y is equal to I times k squared. But now we can integrate both sides, the left-hand side with respect to capital Y, the right-hand side with respect to k, and that'll leave us the following thing. So we'll have the natural log of capital Y is equal to I times k cubed over 3 plus some constant. Now let's exponentiate. So exponentiating, we'll get capital Y is equal to, well, a constant, which we get from the e to the constant, but I'll just rename that c. And then we have e to the I k cubed over 3. But this is not the solution to our differential equation because this is the Fourier transform of y, which means to get our solution, we need to apply the inverse Fourier transform. So let's do that, but let's recall that the inverse Fourier transform is given by this integral. So here we have lowercase y is equal to 1 over 2 pi, and then the integral from minus infinity to infinity of, well, uppercase y times e to the I kx. Uppercase y has this constant in here, which I'll bring out. And then we'll have e to the I k cubed over 3 times e to the I kx. So that's going to be e to the I k cubed over 3 plus k times x dk. Okay, great. But now let's say we weren't really so worried about what the constant was out front and we just wanted to take the constant to be equal to 1. Well, then what we have is a special function here. So this function is known as Airy's AI function, and it is a function of x. And you might notice that we've kind of stopped doing calculations, and that's because this is one of the simpler forms for this function, defined in terms of this integral. And that being said, there's another maybe classic way of writing down this function, and that is in terms of a power series, based off of the power series solution that you would get in a first course in differential equations. And you can compare those two solutions and notice that after doing some calculations, you'll see that they're the same. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.